Okay, so we're going to get started. Now we're going to get into the focus topic, which is the triple I-Girder bent cap system. We're going to go through and talk design, fabrication, and construction. I'll ask that you hold the any questions until after the end of the focus topic. Did you want to do now or wait till John gets in? Okay, we'll do that later. We've got something else that we're going to do. So, all right, have at it. Thank you.
Good afternoon, everybody. There we go. Good afternoon. My name is Nico Kalos. I'm with LJ Engineering, and I'm here to talk about the triple I-Girder bent cap design that we did in San Antonio for TxDOT. Before I get started, though, I just want to say that, to the best of my knowledge, I was one of the last EITs that Doug Spruill ever mentored. And talk about a cheat code to a great career. He was a fantastic mentor, and he has a lot to do with why I'm standing here today. So it's just amazing to see how many people he's touched, and, we'll carry the torch on for him. So let's get into it. So we've talked a little bit about this already today with many of the different presentations. Fracture critical designation is gone now, right? Although some of us, I know even Dr. Hellwig still slips up and calls it fracture critical, but it's non-redundant steel tension membrane, NSTMs. And there's three ways you can achieve that redundancy, right, that we're looking for. Number one is the load path redundancy, which is, three or more primary load carrying members, which is what a triple I-Girder bent cap is, right? Number two is system redundancy. And that's a lot of the things we've seen with those, twin tub girders, how much redundancy that they have that we're not really accounting for right now. And I know TxDOT's working on getting some better guidance out there for us practicing engineers on how to prove that they have that redundancy. And also internal redundancy, which is some of the stuff we've seen with the traditional stacked box caps with these cover plates and stuff like that today. So traditionally, we all know what straddle bents are. Normally when we need a steel cap, for whatever reason, they've traditionally been box caps. And, they have some good advantages. You can get real long spans with those caps. Inherent to any steel bent cap is you have a very quick closure period to erect that cap if you're over live traffic. Very fast, right? You can probably do it in the night. As opposed to like a cast in place post-tension cap, which may have multiple closures for multiple stressings. And so, steel definitely has that advantage. They're easy to transport and erect, right? They're light. They're easy to be, lifted and also trucked across our highways. They have reduced load on their substructure and our foundations, again, because they're light. And the other big advantage that box has is they have the high torsional stiffness, right? And that's something that we like, especially when you have simply supported superstructure framing in. So some of the disadvantages, of course, are those higher costs because they were classified as NSTMs. They are classified as NSTMs. So they have to be fabricated to much higher quality, much higher tolerances. The fabrication has to be done in a confined space. Some folks already touched on that. You have to get inside that box, preheat and so on. So that just drives up the cost. And, because they were classified as fracture critical, there's that, 2-year inspection that they have to have. You have to have, better Sharpie, V-notch test requirements, and your fabrication requirements are higher. And that's historically been the biggest disadvantages and why you only use them when you absolutely had to, right? So that brings us to the project where we implemented these on. This was for the Loop 1604 I-10 interchange. It's a part of a larger project called the North Expansion Project. Obviously, the owner's TxDOT, and this is a 23-mile long corridor, and it's chopped up into 6 segments. And the interchange between I-10 and 1604 is an existing cloverleaf style, very inefficient for the traffic volume that it's seen. And And so in segment 2, we replaced that with a full 8-direction DC interchange, modern interchange. It had a very tight design schedule, 12 months. And so you can see the project team there. So TxDOT's the owner, LJ was the prime, Williams Brothers was the contractor, and the fabricator for these caps was WW AFCO. So as we were going through the challenges of the project with TxDOT, one of the things that they really want us to focus on throughout bridge construction world that was how can we minimize traffic impacts, right? Because it's a very busy area. Right there at the interchange, University of Texas San Antonio is right there. Six Flags Fiesta Texas is right there. They all have access from the frontage roads. Those two institutions have some big traffic generation events, like I think graduation, for example. And so they really want us to focus on how we can minimize closures on the frontage roads. So we did a comprehensive ABC study for all the bridge elements, not just the straddle bents, but obviously the straddle bents are what we're going to focus on here. So this is a preliminary exhibit that we put together to identify every straddle bent we had on the project and to determine, did it constitute a good candidate for some kind of accelerated bridge construction treatment? Some of them didn't make sense. Like, for example, you didn't have any live traffic underneath it in the interim condition, so you could use a cast-in-place cap there. But we went through the whole thing. Some we thought would be best for precast, but others were steel. We identified, especially the ones that were over the nodes, the kind of at the ends of the frontage road. We thought that steel made a lot of sense given the span lengths and also, trying to keep that closure window down. And you can see here that we had identified 7, and we ended up with 9 caps, steel caps on the job at the end of the day. By the way, that exhibit was done about 3 months into that 12-month design schedule. So we had no idea we were doing these caps until, 25% of our time had burned. So that's something I'll kind of talk about and how we had to deal with that limitation through the design. Once we had identified that there were steel caps that were good candidates, we were aware, TxDOT was aware of the cap that's been shown a few times on I-91 in Hartford, Connecticut. Ronnie Medlock and Mike Como were a tremendous help to us. We reached out to them, got a lot of information, some plans, lessons learned, and we it gave us a tremendous head start. But we had some differences between their caps and ours. So they had a continuous trap box girder unit to support, whereas we had all simply supported concrete girders, TX girders. So that meant that we had to deal with an eccentric loading where they had their center line of bearing right at the center line of the bent cap. We also had caps, because they're at the gores, we had to have there was very limited place where we could put our columns. And so as a result of that, we ended up with some caps that had overhangs. And so therefore negative moments also in the cap. We also had a little bit longer caps than they did. Our max was 113 overall, and that had an 85-foot center-to-center column spacing. And then we also had to deal with a couple of instances where the superstructure above was a different height from the forward span to the back span. So as an example, we had one situation with the TX54 on one side, TX70 on the other. So we had a big vertical difference with the superstructure that we had to deal with. So we're going to kind of go backwards and build up the cap. The columns were these aesthetic concrete columns. All the steel was A709 grade 50 weathering. So that's why you see we had the drip plates. I know this is something that's come up that's hotly discussed, is how many bearings. We use 3 bearings on ours, one under each girder. And of course they had a sole plate there. And those bearings are modeled right after the TxDOT standard SGB bearings. I think there was only one case where we had to actually add a couple layers or something like that. But for the most part, we were able to use standard ones. There's our 3 I-Girders. Up on top of the cap, we have different components to help us support the superstructure. So where we could, we use these things we call them masonry plates after what you use on a pot bearing. And you can think of that as like a typical TxDOT concrete bearing seat. That's basically how we modeled those plates. Where we had a big vertical difference, we actually built up pedestals. So on that TX70 to TX54 scenario. And then underneath those plates or pedestals, we would group them under a bearing plate. Dr. Hellwig referred to it as a batten plate in his presentation. And those are there to support those plates and also help seal off the drainage in there. And then where we didn't have any plates, we put sealer plates, non-structural 1/4-inch plates to keep the water out. Inside we have our stiffeners. The intermediate stiffeners did two things. One, they supported the flanges underneath where we had those concentrated loads coming from the superstructure. And they also acted as a support location for the diaphragms. And that's a very, very important part of the design of these caps are the diaphragms, which we'll talk about at length shortly. We also had bearing stiffeners, pretty standard there. And we had jacking stiffeners to help, if you need to replace the bearings. So there are the diaphragms. We didn't have a diaphragm underneath every girder coming from above. And so where we had just one, single isolated girder there, we would have just a transverse stiffener. And you can see that they have a inspection access built into them. And then at the ends, we had, cover plates. One end had no door and the other end has 2 inspection doors. And we used FRP grading at the bottom. We attached it with clips, so there was no drilling into the bottom flanges. And we liked FRP because we could get very, very small hole size. I think there were 3/4-inch holes, so that'll keep hopefully the majority of birds out of there. You're not going to stop the insects, but and then up on top we had our elastomeric bearings for our TX girders. So that's kind of the anatomy of the cap. So the masonry plates, I'm going to talk about a few of the little details. The typical one was beveled, to follow the slope of the cap. Something to remember is that these caps were used in gore areas, which meant that almost every one of them had a cross slope break in the cap somewhere. So we had variable slopes. So where we could, we tried to use stacked plates before we went up to those pedestals. So we could use one plate if the thickness was less than or equal to 4 inches. After that, somewhere between that and maybe like 6 or 7 inches, we would use a sandwich. So we'd have one plate that was beveled, and then we'd have a flat plate on top. And we kind of proportioned them to fit a typical TxDOT bearing seat, depending on the angle that's coming in. That's how we figured out that width, along the axis of the cap. Those bearing plates, I get this question a lot. We did not consider the bearing plates for any structural resistance capacity. And there's no bevel on them. They're 1-inch thick, uniform, and we did try to group them as much as we could to try to get some economy of scale. I don't know if it really did get any, but we tried to group them as much as we could. Then we had the I-Girders themselves. We had 9 bent caps. So if you take one bent by itself, it would have maybe a different web depth or a different flange width. But the 3 girders in each cap were identical. We had no changes of any plate thicknesses throughout each cap. We wanted to keep it simple. Remember that we're dealing with a very short amount of time to design also, and we had 9 of them. So we kept it simple. And we did have to set some limits. So really stuff was driven by primarily inspection access. So we kind of backed out, okay, well, our minimum flange width is 2'9", and our minimum web depth is 5 foot. We did have some caps that had a web depth of about 8 feet as the deepest. And we set some limits, starting points for each team for their flange thickness and their web thickness. So let's talk about the design a little bit. We kind of started, and we hadn't done one of these before. So we had to kind of start from the ground up and think about how how do the forces flow through the structure, and then what do we need to do to design for them. So I'm going to kind of walk you through the process that we went through to figure this out. So we start with a very, very simple model, single beam model, and we have a point load and a point torsion throughout there, right at each point there. And so what that does is it generates a very simple moment shear and torsion diagram, right? That I think we can all very quickly pick up. So you're going to have a maximum positive moment and you're going to have a maximum negative moment over that support there where we have the overhang. And so, that's obviously a very simplistic view, but it helps us understand how this thing behaves with the three girders. So the next, you can see our grillage model, where we actually took three girders and we have modeled the diaphragms, and those are the transverse elements there connecting the girders. And they have a real stiffness in this model, right? They're not infinitely rigid. They have a real stiffness. So what happens then? Well, we see the middle girder, which is M2. So the first girder is M1, middle girder is M2. M2 has about a third of the moments, about, close. And I should mention that the load in this instance is actually placed at the center. So later we had to deal with it being eccentric, but right now we're putting it at that center girder. And that's probably what you would expect. It has about a third of the moment. But you can see that M1 has got 50% of the moment from the previous model, and M3 has only 17%. And that's because of that torsion, right? What's happening is that torsion is resolving into a couple. So the outside girders are acting kind of like the webs of a box, kind of, is what's happening, right? And they're picking that stuff up. So, and you can see that in the shear diagrams as well. And it's more clear there. One has more shear and one has less. So then we said, okay, let's really kind of split it out a little bit more and really try to understand where all that's coming from. And you can see here, this is kind of summarizing what I just said. The way it's going to deflect with that load right in the center is that the middle girder is going to deflect the most, a little bit more than the other two outside. And the amount of that relative difference is going to be a function of the stiffness of the diaphragms. The more stiff they are, the less relative movement there's going to be. And if they're infinitely stiff, you would see a perfect third of the moments in this model where you're not applying any torsion, right? So it's just vertical loads. And you can see that here, but these have real stiffness now. So that's kind of an example of, what we actually used, where the vertical loads are mostly distributed, pretty well, but that middle girder still picks up the most. And then if you just isolate the torsion, you can see how that affects the outside girder. The middle girder obviously gets nothing, and those outside girders are equal and opposite. So we had to decide how we were going to model it. These were kind of the different things we thought about, how we could go about it. Obviously, I think all of us would probably love to do that E model right there, full brick, 3D FEA, but there's no way we had time to do that. So we ended up going with the grillage model. They've been used for a lot of steel structures over the years, and especially there's no curvature here. We felt like this was a pretty good one, but we had to validate how we were going to do this and make sure that we were capturing all the effects well enough, or make sure that where we weren't capturing them well enough that we were conservative enough, to feel comfortable and get the designs out. So we ended up going with the grillage model, which is B right there, where the diaphragms are going to be modeled as a beam element that it has a rectangular cross section, so basically a plate. All the modeling we did was in STAD Pro. We did do a little bit of Midas modeling to kind of confirm things here and there, but pretty much everything was done in STAD. Here's an example of what it looked like. We didn't actually have the models with the columns in there. We did just put pins, but this was one that we had. I think we were kind of testing some stuff, and we went with a big, full-blown model there. And you can kind of see what I'm saying there, that you have, the girders themselves are modeled with the exact dimensions of the girders. The diaphragm are modeled as a fictitious plate that has the equivalent stiffness of the real diaphragm. And the girder loads from above came in eccentric to that middle girder, and based on the difference between the center line of the girder and the center line of bearing for the two spans coming in. We did have one expansion bearing and one fixed bearing that allowed the cap to expand transversely to the bridge. And we put that bearing underneath the support that had the most load coming in so we can maximize the normal force just to make the bearing designs a little bit easier. So the diaphragms, they're key. They're the key to this whole thing. So we had to figure out how, how do we come up with that stiffness, that equivalent plate? So what we thought is that, hey, this is really, it behaves like a Verndale truss or a Verndale frame, if you've ever heard that before. If you're not familiar, it's a frame that carries moment, a truss that carries moment. It's not really a truss, but they're used in trusses a lot. And so, that kind of idealized down into something that looks like that. So what we did is we did one full-blown FEA analysis. We applied a load at the center girder, and we calculate U3, that displacement, that relative displacement. So then we came back to this Verndale model, and we said, okay, we figured out a way to come up with some analytical expressions to calculate U1 based on, the actual diaphragm plates that we're putting in there. And we found that our analytical expressions matched very well with the FEA model. So we felt, okay, hey, this is good. This is close enough, right? So then we still needed to get to that plate thickness. So once we did that, we came down and we basically modeled this like the diaphragm is this simple span between the two outside girders. And there is a spring, though. They're not fixed. There's not a pin right there. There's actually a rotational spring that's a function of kind of the fixity in that direction, right? Which is, again, a function of that girder on the outside. So we had come up with some expressions for that, and we found that, based on this depth HD and thickness TD, that in our expressions, U2 was coming very close to U1 and U3, and therefore we had kind of figured out how to come up with those plates. So as far as design checks on the main girders, they're relatively, if you've done plate superstructure girder, design, very familiar. It's not much more to it. We did, obviously reduce our bending capacities for some of the lateral bending that's occurring due to the torsion and the outside girders. They do get a little bit. They all kind of rotate slightly, especially when they're unbalanced. And it's like Dr. Helwig was saying, they're kind of pseudo closed. They're kind of in between a closed and an open section. Again, we did not consider those plates on the top as providing any stiffness, support, nothing. Just the weight. That's all we took from them. We considered things like, flange plate buckling, local bend buckling of the web. As far as shear design, we considered the webs unstiffened. And, we also proportioned the web and the flanges based on straight girder limits. And obviously we had to check, for fatigue, and we had to check our welds and everything like that. But those things are really not that much different than what you do in a box cap. The modeling is what we felt was kind of the biggest challenge that we needed to solve. Our stiffeners, they had to have kind of a flare in them because of that inspection access, but we needed to support that full upper flange where that concentrated load from the superstructure was coming in at. So we had developed another kind of analytical free body diagram to help us design those stiffeners. And we verified that with the FEA model. And you can see that the way the stresses kind of flow, it very closely mimics our kind of free body diagram concept. So, that was just something that we had to deal with it. Again, if you were to go wider with the cap, which some folks see as a downside to these caps because they're already pretty wide. You saw how the column had to be rotated 90 degrees to what you normally would see. So that long axis was actually along the longitudinal axis of the bridge. So if you go wider, you could probably eliminate this, but in our case, we needed to do something like that. The diaphragms, again, okay, we figured out how to come up with their stiffness, but now we have to design them. And we could have gone crazy and did some, every single one of them put into an FEA model. We did a few, some of the highest loaded ones, and just verified that, again, going back to our Verndale analog, that we were capturing things properly, and that's what we used. Here is one of the areas where we were seeing that sometimes the maybe in some hot spots, we were a little under predicting what the stress was going to be in those plates. So we backed off quite a bit on the allowable stress. So we really backed off on what we were going to, we didn't push them very hard at all for that reason. Again, because we were on a very compressed time schedule, and that's just the reality of a design consultant. We also had, miscellaneous things we had to check. I'll tell you that live load displacement is something you should check right off the bat. And check your deflections, because that will likely govern the depth of the cap. That, I think, on every case that was larger than that minimum for inspection access, it had to do with the live load displacements. We had to design our pedestals. There's nothing cutting edge there. We had to do some plate bending and stuff like that. Another thing we had to consider is that some of the DCs were not going to be both erected at the same time. So you'd have one DC that's open to traffic while that future DC has not been constructed yet. And so that's something that we had to be careful about when we designed our bearings. Again, that normal force, you got to make sure you have the full range of what's going on in there. And also with torsion, right? That's also another torsion issue that you have to deal with. Am I doing on time? I'm doing good. So here's a few pictures of them. They're in the fabrication shop, and you can kind of give you a sense of scale, how large they are. They're all weathering steel. They're nice and clean. Just got blast cleaned, and you can see what that inspection access looks like. I get this question a lot as well. Did we paint the insides white? We did not, and that's something to think about. But kind of going back to what Jason Lloyd said is that we're not very good at finding those cracks, and these are redundant members. So if there is a large crack, we'd be able to find it, right? So we didn't paint them white. There's another good shot, kind of close up. You can see what those masonry plates look like. You can see the bevels there. That's the bearing plate. One thing is that I noticed seeing them out in the field is that they were shipped with all three girders bolted up together, but for whatever reason they didn't ship them with the bearing plates or the sealer plates. They actually came on a truck separately, and they put them together on the field. You can see the FRP grading down there with those clips. So there's no drilling in those flanges. And there's a shot of the first two that were erected. They've got superstructure on them now. And you can see these ones did not have the largest overhangs, but they did have some. I think those are probably about 10 feet or so. And they're back to back. One of the things we were worried about is aesthetics and how this thing look. We had done some early 3D modeling like what you had seen on those previous slides, but I think they came out great. Seeing them in person, it's hard to tell that they're not a box really, especially when they're up in the air. You can't tell how much those flanges are sticking out as well as I thought we would be able to. So I think aesthetically they look pretty good. So we're on hold for the next one or wait for the questions? Okay.
All right, thank you.